Ella and Fred asked me to give an introduction to the virtual brain, and I actually want to do this in the context of e-brains. So e-brains being one of the outputs of the Human Brain Project, aspiring to become a European infrastructure neuroinformatics platform that is being rendered permanent, and it's on a good track with regard to this. And it already exists, it has been established. Yeah? Virtual brain being one of the simulation engines that have been integrated in eBrains. The virtual brain, however, has been developed by now something like 10 years ago. That was Randy McIntosh at that time, myself, Petra Ritter joined us, and this group, in the context of a James McDonald grant, developed a neuroinformatics platform enabling the construction of macroscopic brain network models linking directly to brain signals. And that's what I want to show you here without much introduction. So it's an open source neuroinformatics platform available since 2012 and has become now one of the primary simulators in eBrains, because it actually makes a nice link between source signals and brain imaging signals, as I'm going to show you. Yeah? I said macroscopic level. Here you see brain structure and brain connectome as extracted for the human, typically from MRI. You get the surfaces here on the left-hand side, the connectome on the right-hand side. You can co-register it in the same space. And build a network out of this, making particular parcellation that then generating individual network nodes connecting through the individual connectome, spanning it in three-dimensional space. That provides you with the source space, yeah, and which can then be equipped with mathematical equations that are rooted in mean field theory. And I will not say too much about mean field theory, since later there will be a talk by I think two people, Matti Develo will speak about that. And essentially what we are doing in mean field theory is we are taking individual neurons and using statistical physics in order to map this upon collective variables, such as we know it's from statistical physics, such as temperature, heat, pressure, variables that do not exist on the microscopic level, but are very meaningful on a mesoscopic level, allowing us to build macroscopic models. Keep in mind the discussion that we had around Fredo's and Alain's talk in the beginning. Yeah? These entities become the neural masses, or are called neural masses, and become the network nodes in this form of brain network. And that allows us then here in this cross-section, you see it nicely represented. We have a parcellation in there, and we have source signals that can be measured either via LFP on the microscopic level, or more macroscopically with ECOG directly on the scalp, next to it, the electroencephalography or magnetoencephalography, allowing us on outside of the brain to measure large-scale signals. So we have a source to sensor mapping that needs to be taken into account, which is also being integrated in the virtual brain for a variety of brain imaging techniques, such as gold signal, such as EEG, stereotactic EEG, MEG, and all these can, depending on the machine, can be personalized. Yeah? So summarizing, we reconstruct the cortical and subcortical surfaces, we parcellate, we equip it with mean fields for each individual parcel. In this representation, we are typically having 100 to 200 individual neural masses. These are typical numbers that we're dealing with. Then we connect it with an individual brain connectome derived typically from DTI. And then mapping it forward in epilepsy, what we're doing is stereotactic EEG, so individual needles that you see represented here, collecting activity at these macro electrodes at the spacing of a few millimeters, or MRI, functional MRI imaging. Yeah? I wish to direct you to the platform itself on the website. You can either operate it with Python notebooks, which is what you do typically in the long run. But to get started, you work with these individual interfaces that allow you the manipulation of the connectivity, a treatment, pre-processing of the imaging data, selection and parameter setting of the individual mathematical models. Parameter setting is very important. That's actually an issue. Even parameter sweeps are being possible in there numerically. And then running simulations and representing data on the source level, or here as an example on the EEG level, and plotting them as you do it typically in individual experiments. Yeah? So that is for the virtual brain platform. You can do it for the human. You can do it for the macaque. Randy and Kelly later will speak about the macaque brain, or for the mouse. As an example here, mouse and mathematics is identical. Yeah, you have nonlinear integral differential equations with local dynamics and global connectivity kernel given by the white matter connectome. Just as some examples, this is the advantage in the animal model. You can use different forms of connectome. Here you have probabilistic tractography, the same mouse deterministic tractography, or coming directly from the Elm Atlas tracer-based connectivity. And the reason why I'm mentioning this, given the short time, just want to highlight a few things, is you can actually nicely in this platform connect or build individual virtual brain models using different connectomes and actually study them systematically. Yeah, when you can do it with the Allen connectome. There, the tracer data are coming from multiple mice, so you use the individual information, but you have very high resolution and can build the virtual mouse brain, generate data such as you can measure it in the bolt for the mouse, for instance, in a mouse scanner, and then build your favorite metrics. Here's an example of functional connectivity. You can do this then also and compare it against some of the data coming from the various DTIs, then build a DTI-based mouse, or for the human, a DTI-based human brain, and generate, again, simulated bolt data and build your favorite metric that you can actually compare against the empirically measured data of the mouse in the scanner. Yeah, in this case, we worked with 19 mice in high resolution scans. Yeah? So this can be done. I just want to highlight the result. And what you see here is you do scan rescan of the functional connectivity. You go for a single individual, you come up to about 55 to 60% predictive power of one scan for the other. When you do it with a tracer-based connectome, which is a high resolution connectome, you get actually the best predictive power. And when you compute this, it's about 80 to 90% of the scan-rescan variability. We can discuss how bad functional connectivity is as a metrics, but there are other metrics that can be used. Here, just the example of functional connectivity. And then you can do this for different connectomes. The individual connectome, yeah, as you see for different technologies, individuality wins, outperforms other than surrogate connectomes. Can also start taking the tracer connectome and start manipulating it. Yeah, you can filter it so only the type of connections are involved, like in the DTI. Yeah, or you can symmetrize it because DTI is symmetric. So you see the following: high resolution outperforms individuality, and individual connectome outperforms generic connectome, yeah, or average connectome was average surrogate. Yeah, keep this in mind. So high resolution has predictive power, obviously, and individuality has predictive power also. What we do in e-brains and generally in the virtual brain is the following. We take this information, the fact that we can actually individualize virtual brain models. We build them based on individual connectomes. We equip them with added information that we have available for the human, or if we can go into a higher resolution like we did here for the mouse, or we are able to do within eBrains by providing additional information, then we can build a generic model, and then which is individual, and then run it against empirical data, functional data, in order to further fit the model and optimize the model using not only artificial intelligence, but intelligence techniques. In our hands, this is typically Bayesian inference techniques to sample the parameters that are specific for this particular individual to build an individualized brain model, which we can use. And this, in our hands specifically, we have done along the example of resting state and also epilepsy. Epilepsy is the most advanced one, where the functional data are typically pre-ictal, ictal, and post-ictal data, seizure propagation data that you see represented here for an individual patient, intracranially measured. We can equip the brain model with a personalized implantation, put all maximum of information we have in there in order to bias the parameters, and then actually run it on retrospective patients. Now we are running it on prospective patients. We have an ongoing clinical trial, and at the moment, the last time I looked in February for the HPP review, we just passed to, we had 128 patients. So in terms of performance, again, it's difficult to find good metrics for performance. There is not one metric, so we use a whole battery of different metrics, sensitivities, specificity, or here expressed in terms of precision, recall, so binary types of classification metrics. Generally, you find the following message. As compared against clinical hypothesis, which is what you find here in terms of AUC value, we are at around 75%, for instance. This is a spread of around 50 patients. When you compare it against outcome of the surgery of the epilepsy patients, 13 were successfully operated, and this year is a precision value around 80% for the patients against clinical hypothesis, and this year is against what is coming from the virtual prediction. For the non-successful surgeries, stays around 75%, the surgery that has been performed, and drops for the virtual brain, which gives us hints about actually the potential predictive power and new avenues proposed by the virtual brain of how the surgery could have been performed. And since it's a prospective trial, we have two branches, one in which actually they will get the information from the virtual brain, trying to bias a trial, and another branch in which this will not happen. The results we have to wait until 2022. So this is what we can do. We can now build the individual virtual brains composed of these network nodes, as you see here in blue, build the virtual brains and run seizures once parameters have been fit. And this here is a simulated seizure mimicking the seizure propagation of a particular patient with the epileptogenic zones identified here, highly personalized. When we do this, and now I'm going beyond this trial. So this is the current state of the art. We know that there are many shortcomings with regard to this. And some of these shortcomings can be overcome by making use of eBrains and the capacities we have in eBrains. Five minutes until 20?
Yes, exactly.
Okay, I better hurry up. Thank you. So this is, we have huge, with this parcellation I was talking about, huge region sizes, about 20 square centimeters. And there are large issues in terms of source to sensor mapping. So the resolution is on the multiple centimeter levels. So we go we want to go to higher resolutions, which requires computational power. Yeah, this is where eBrains comes in. Then we want to bias the individual regions with loads of information, because in HPP we have developed a very detailed and sophisticated mean field models, and they're allow us in the lead of this, yeah, that can be actually be informed by additional information coming from cytoarchitecture, neurotransmitter distributions. All this is information is there. It's being curated, the data, organized, and made findable within the brain reference framework of eBrains. So building a knowledge graph. So it's not just a database, but the data is actually organized and mapped upon a three-dimensional space, which is an atlas for the human, and we're talking about the human now, yeah, and allows actually to access this information either again through a graphical user interface or by manipulating the knowledge graph, yeah, and that links to the world of simulation engines, allowing us to make actually use of this type of information. eBrains also provides not only the simulation engine, but also the basic infrastructure to operate all these tools, the analysis tools, the model building engines, but the hardware to run the simulations, and all the software to organize the information that is available and map it back upon the models. Yeah? Just an outlook for what can be done. We can go now to a high resolution, 20,000 or 260,000 nodes, which allows us actually to talk about the type of neural fields we discussed early in the beginning of this workshop. Yeah? And then we can equip it with dipole moments perpendicular to the surface and actually perform proper forward solutions from the source to the sensor space, yeah? Which allows us to sample, for instance, the human hippocampus in much detail and actually make the continuation from the cortex going directly into the hippocampal ending here. Yeah? And here you have an example of a reconstruction of the hippocampus where one of the SEG needles is being inserted, and we can actually map the forward solution directly on these sources. And that allows us then to build the type of neural fields with we discussed earlier this morning with intracortical connectivity and mimic the white matter connectome and look actually at the propagation of the individual seizures. And we already have first patients that are demonstrating some results. This is patient data where the activity propagates across the surface and taking the conditions of the seizure data that we have, of how the SEG is organized and implanted, and the mapping of this cortical surface, as you see here. Many conditions have to come together in order to be able actually to identify in the human such a traveling wave. For one patient, we were actually able to have all these conditions, and you have a very nice overlap of the simulation and the recording here. Yeah. And then you can do this type of simulations as we saw in the monkey earlier, propagating waves starting at the epileptogenic zone and propagating temporal pole here in this case along the temporal cortex, equip it with high resolution connectivity that we can get within eBrains. And this is mouse now, because this is not being done. Michele Migliora is working on this, actually construct very detailed hippocampal models in this case, using the NEST simulator, where we can actually combine in the eBrains infrastructure also different simulation engines to perform what we call co-simulation. So NEST and TBB together, mean field models and detailed models, in order to see the propagation actually also on the highly resolved microscopic models. Yeah, in co-simulation. And I conclude, and why don't I stop here?
So right in time.
Thank you. Yeah, thank you for your attention.